So welcome to part 3, where we're looking at the Gossen Metrawatt Ultra. This is the model M248B. In this video we're going to be looking at the continuity test, and we're going to attempt to write some software to interface with the meter, and maybe we'll try doing a temperature stability test on it and see how it compares against this UT181A from Unity. I also sent Metrawatt a second letter, and I provided them with an update on how I was doing the testing on this, and mentioned that part of the problem may be a sensitivity to a static field. And I also provided them with a link to the video that shows the testing that I've done so far. Unfortunately, I still have yet to hear anything back from Gossen. So I did test the continuity feature of this meter. This particular one has a open circuit voltage of 4.1356 and a short circuit current of 1.032 milliamps, which I believe is quite high. With a 50% duty cycle square wave, this meter could read all the way up to 9 Hertz before it would start to miss. So it's certainly not the fastest meter that I've tested, but that would be sufficient for the work that I do. The minimum pulse width that it could detect was 250 microseconds. I think what I'd like to do next is try to communicate with the Ultra using a Bluetooth interface. This is a small adapter made by Targus. This is a part number ACB10US1. This is a Bluetooth 2.0 adapter. You can see it just plugs into the USB port. I'll just go ahead and plug it into the PC. Alright, so down in the lower right you can see we now have a Bluetooth icon. And we can see that Windows 10 is now searching for devices. And we can see unknown ready to pair. It's asking me for the passcode, and that would be the pin number that I've entered into the meter. In this case 2017. And we can see it's found the Metrawatt Ultra Bluetooth BB1668 paired. So now we can go more Bluetooth options. And we can select the COM ports, and we can see the outgoing port is defaulted to 17 and the incoming port is set for 18. So this is the LabVIEW software that's supplied by Metrawatt, and we can see they have some different libraries. Request a temperature unit, get selected clip factor, get a value, get the value in the range, get the device identifier, get the battery voltage. It seems fairly inclusive, but you notice at the very top for examples they have a example VI. So let's go ahead and run that, and what we would do is change the COM port of this to 17, I believe, and now we can just hit run, and you can see it's now collecting data. Alright, so what I've done is I've attached this to my function generator, and I'm outputting a sine wave right now, and as you can see it's recording that just fine. So it looks like it'd be fairly straightforward at least to do data collection with this meter. So let's just try to go ahead and put together a small LabVIEW program for it. Alright, so this is the little program that I put together for the Gossen Metrawatt. We just start this thing. You can select the communications port, so we'll set it to 17, and we'll hit open. In the upper right you can see this is the multimeter's temperature. This is internal of the meter, and this is the battery voltage being displayed. And across the top we can see it's a Metrawatt Bluetooth Ultra. You can see its identification number M248B, and here's the serial number and the software version number. We'll select the main plot. From here I can plot the temperature of the meter. We could also plot the battery voltage, or we can plot the meter's input. We can see it is selected to volts DC. This is going from -1 volt up to +1 volt, or 2 volts peak to peak. In the top center you can see I have a record button, so I can collect this data to a CSV file and import it with other software. I can just read it back into this program and post-process the data that way. Across here we have the standard deviation, the mean, the min, the max. So you can see our maximum voltage is 1.005 and the negative is minus 1.0007. So there are some quirks with this software. This is one of them. There is a program to read the stat, and unfortunately they don't define what stat does. I know it returns 4 bytes of information. I started to try to decode some of that. It does appear that bit 0 of byte 2 is the relative and bit 4 is the min-max, but beyond that I'm not 100% how those bits are being defined. So we can see if I select the min-max of the meter, and that will illuminate the min-max light. Let's try to go to resistance. You can see it's displaying resistance here. So I hit the 0 rel and now I get the rel. So there, it's off, and 0 plus rel. Now it's illuminating. Unfortunately, there isn't a manual on their website that defines all this, so you're just kind of left to your own devices, I'm afraid, to sort this out. But all in all, it seems fairly straightforward. If you just need to be able to get some data out of the meter, that should be fairly simple to do. Now that we have some communication software written for the Metrahit, what I'd like to do is a temperature stability test on it. I ran that test before with all the meters that I have. This Unity UT181A, believe it or not, is the most temperature stable meter of all of them that I've purchased. Unfortunately, we can't say that for the UT61E. The only meter that drifted worse than this was the X-Tech EX540. So I did a video where I temperature compensated this. I think I varied this meter from like minus 20 or something up to 60 degrees maybe, and this meter is very solid now. So recently I did a temperature drift study on the UT181A where I held the ambient temperature constant at 27 degrees C. And when I say constant, I mean less than plus or minus 0.01 degrees Celsius. So what I'd like to do is repeat that test now for the Gossen Metrahit, and let's just see how stable this is compared to the UT181A. So to run this test, all I have here is a meat packing box. You can see it's foam packed just like a cooler would be. On the inside I have a second cardboard box, and this is also foam packed. And down inside you can see I have a fan with a series of resistors, and I'm just using this as my heat source, obviously. And then I have my temperature sensor. This is not a thermocouple, this is a platinum type RTD, and this attaches to my 34401A, and then I just basically use LabVIEW to do all the math calculations to convert this into a temperature. So this just sits down inside the box. I'll put the meter inside and I'll enclose this. Then what we'll do is just run the temperature up, and hopefully we can hold it fairly steady inside the box, and we'll just see how much that Gossen drifts. This is looking at some temperature data that I took off my Unity UT181A. This was about 16 hours worth of data, and this is where I start up the meter here. This is where it warmed up, and then I basically just ran it for 16 hours, and then I opened up the windows in my office and I opened the box, and then touching the meter caused these huge spikes here. But basically the meter only moves a few counts. Each one of these counts represents 1 microvolt. So from here to here, this is 1 microvolt, 2, 3. So you can see it's about 4 microvolts peak to peak total up until we get out into this area here, and you can see it increases quite a bit. But again, if we weren't disturbing the meter, at worst case I had this one spike here which would take us to 5 microvolts peak to peak. And over here where I opened up the windows and I had the fans blowing, I was able to get about a 10 degrees C differential from this point to down here. So this is looking at the Gossen Metrawatt So I tried to run the test the same as what I ran the 181. So I had set the temperature for 27 degrees. And unfortunately my office temperature has been heating up now that we're getting into the summer. And this is actually a drift of, it's under a degree, but it's still about maybe 4/10 of a degree. And that's causing this error with this Gossen. So if we zoom into this area here where it's semi-flat, so up here this is 15 microvolts, and this is all the way down to 22 microvolts. So you can see that the Gossen has quite a bit more peak-to-peak noise, even with the temperature being stable. If we zoom back out, what I've done here is I've gone from 27 degrees C and I increased my temperature to 30 degrees C. So this is looking at our temperature over here. This is the room temperature actually varying, and I'm not able to regulate. And here you can see I've increased the temperature to 30 degrees C. I'm actually able to control the temp. So the real problem is not so much this instability. The problem here is that the meter has just stopped talking. You can see there's nothing. If I go ahead and close the port, let's try to reopen. Yeah, nothing. Here we can see the meter's paired. Let's try to remove the device. You can see now we're trying to locate the meter and it's not finding it. Let's just have a look. You can see what went wrong with our meter. It's hard to believe it would have failed just running at 30 degrees C. Yeah. Have a look here. You can see the meter is actually turned off. Let's just see if it'll turn back on. Here you can see our problem. It looks like the batteries are dead. So that was a full charge using 2 nickel metal hydride batteries. I don't know if the meter just shuts down when the battery voltage gets too low, but possibly using the lower voltage nickel metal hydrides are causing the problem. I mean, I would have thought this meter would run for quite a bit longer than what it did, but at least it's not like a software problem or anything that caused it. It legitimately just turned itself off. So I'm really curious now how much current this Gossen actually draws. I ran similar tests on this SEM-DT9939. I can tell you that when I was developing my software for the Signal Hound to decode the data off of this meter, I probably ran this thing for about a week. And towards the end of the development, the battery in this was starting to fail, but it was nowhere near 24 hours like what I'm seeing with this Gossen. That's just crazy.
Gossen really know how to design industrial test gear.
So if we look under battery, this is in their manual for the meter. Here we can see again it's talking about the 2 1.5 volt batteries, and it mentions the 1.2 volt nickel metal hydrides, and that's what I actually used inside the meter when I ran the test. Under service life it says with alkaline manganese approximately 200 hours. It talks about the Metrahit Ultra Bluetooth. When the Bluetooth interface is activated, power consumption rises considerably and the service life is reduced accordingly. So what's considerably? Of course I have the SEM-DT9939, which also has an RF link. When it's just normally running, it draws about 5.06 milliamps. And when you turn on the RF link, it'll draw about 20.17 milliamps peak. If we look at the current when I'm actually communicating with the meter and downloading data out of it, it's about 8 milliamps on average. I'm using currently a Pro Cell in this. This is just a 9 volt transistor battery. That battery has a 550 milliamp hour rating. So this meter would run about 68.75 hours. And that's again with the data link active. That's a significant difference from this Gossen Metrawatt. So the way I have this set up, this Bryman meter is connected up to my powered shunt, and I'll just set this for the milliamp range. And then I also have my UT181A, and this is connected to the amps jack, so this will have a very low burden voltage, similar to what my little power shunt has. The TPI meter is looking at the voltage directly across the meter inputs. So let's just power up this meter and let's see what kind of current this thing actually draws. So you can see the supply voltage is set for 3 volts. We'll turn on our little powered shunt, and you can see we're reading 27.8 versus 28, and this thing jumps up every now and then. You can see a 30 milliamp. So with the meter just sitting idle, this meter is already drawing more than what this thing does. There it is, 34 milliamps. 35 is the Bluetooth module that I'm using to communicate with this. All I'm going to do is install this. So right now I'm trying to pair with the meter. Look at this. 54 milliamps. And that's going to hold that until I actually pair up with the meter. So let's go ahead and do that. Windows is now paired with the meter, and you can see the current has dropped back down to 28 milliamps. Okay, so now I'm running LabVIEW, and I'm starting to record the data off of the meter. You can see the Bluetooth interface is now active. And you can see the meter is drawing upwards of about 63. There's a 70 milliamp peak right there. So the peak currents on this are very high. So again, we're running at 3 volts right now. I wonder if we adjust this down to about 2.4, which would be nominal for the nickel metal hydrides. You can see we're almost up to 80 milliamps. If you look at the Gossen's display, it's showing 2 bars right now. Let's go ahead and reduce this a little bit further. You can see we're at 2.15 volts roughly. And our current is now all the way up into the 80 milliamps. You can see the meter is still showing 1 bar. Let's adjust it down just a little bit further. There's quite a bit of delay on the test, but you can see we're all the way down to 2.05 now. And now we can see currents well into the 90 milliamp ranges. We'll just set the 181 to min-max. You can see right now 102 milliamps. See if we can go any lower. Right there, she's turning off. So about 1.8 volts. But you can see our peak current. We're all the way up to 114 milliamps. It kind of makes you wonder what the peak current is on this thing. What we'll do is we'll just disconnect the Bryman, and I'm going to connect this up to our oscilloscope. Here you can see our average current with the Unity 181A, and currently the oscilloscope is set for 50 milliamps per division. So you can see we are roughly in the center point of the second division up, so roughly in that 75 milliamps or so range. But again, we can see peak currents here well into the 100 milliamps. And this is with a 2.4 volt source. So this would be with a set of batteries that are fully charged. Well, I don't know about you, but I'm not impressed.
These wacky Germans know how to design top quality products.
So these are the batteries that I was using in the meter. These are sold by Energizer. Again, they're a nickel metal hydride. These are rated for 2300 milliamp hours. Somebody's complaining about their calculator dying. It's my old Sharp. You can see the display on this thing is pretty much shot. So if I take 2300 milliamp hours and divide that by our 67, can see that works out to 34 hours. So if my batteries were in perfect condition, brand new, you know, you might be able to squeeze that kind of time out of it, maybe 30 hours or so. But again, this meter dropped out during our testing after I charged up the batteries at about 23 3/4 hours. So yeah, I'm not impressed. I think that's going to be it for this part of the review. Unfortunately, I have yet to hear anything back from Gossen as far as my concerns about the meter. I may give them a couple more days, and then I think we're going to go ahead and start doing the teardown video for this, and we'll see if we can maybe solve whatever the problem is with this meter, or at least identify it.
Gossen Metrawatt are really known for their tough, high-energy industrial meters. You look at all the, you've got your high-voltage fusible resistors here, you've got input protection, you've got a spark gap here, you've got a huge HRC fuse, you've got the nice high voltage slots cut into it here, if you can see that. As you'd expect with a top quality Gossen meter, you get a ton of input protection. Here's some high power input protection resistors, a couple of PTC poly switches here and here. That's your AC input coupling cap. You've got a couple of gas discharge tubes here, surface mount versions, nice to see. You've got a MOV here, and curiously there's a couple of what looks like half amp fuses here, and I'm not sure what they're actually protecting. Your guess is as good as mine.